Didn't ask you either. All right, so one block of the whole course, I will talk about the real number system. The real number system is called that because they are the numbers that we, across the world, use to count. Now, it's called the real number system because there's a whole separate set of numbers that are the imaginary numbers. And I know it sounds like something from Sesame Street, but this is going to sound weird. Imaginary numbers are a real thing. I know, right? But don't worry about them. You don't need to worry about imaginary numbers until second year university physics and calculus classes. Until then, you're perfectly good knowing the real numbers. You don't need to worry about the imaginary numbers, which, even though they are called imaginary, are indeed real. But not really real because they're not, because they're imaginary. Okay? That makes perfect sense, right? Yeah. Okay, so real numbers. We're going to start with the natural numbers, and I'm going to highlight them in blue. The natural numbers are, and this is going to also be weird, the natural numbers are the smallest group. Of all the numbers we have in the universe, they're the smallest group. And here's why that's weird. There's still an infinite amount of them. Okay? Even though the natural numbers have an infinite amount of numbers, they are still the smallest group. Everybody cool? All right. Now, if I were to ask you, like Mrs. Bad Crumble would, at the very end of kindergarten, because in North America you only need to be able to count to 10 to get out of kindergarten. If I were to ask you at the end of kindergarten to count with me, could you all do so? This is not a trick question. Could you all do so? Yes, excellent. If I were to ask you to all count together every time I clap, you could do it, right? Everybody ready?
1, 2, 3, 4, 5, 6, 7, 8, 9.
Just kidding. What did you all start with? 1, right? Every single person started with 1, yeah? Okay. The natural numbers are what I like to call the counting numbers. If someone says, let's start counting, we all start counting with 1. Is 1 indeed the real first number in our number system? No. What is? 0, right? Our numbers go from 0 to 9. And then at 10, you have one group of 9, 10, 0 to 9, and 0 left over. That's how our number system works. Then when we get up to one group of 10 and 9, 19, what's the next number? 20. Two groups of 10 with 0 left over. That's how we count. We count in a base of 10. Now, there's been many other ways to count in the history of our world. The most complex one of those was developed by the Mayan natives in South America, and they counted up to 20. Does anybody want to guess why? It's South America. It's very warm there. Why would Mayan people count to 20, but people in Europe count to 10? Not temperature. It has to do with temperature. Why do we count to 10? We have fingers. What would a Mayan person have? Fingers and toes, all visible all the time. As a matter of fact, the symbol, just for fun, for the number 20 in the Mayan language is this. Because that is a dude going like this. True story. They count to 20. We don't. But now you know that they did count to 20, which is another reason why all that 2012 bullcrap was bullcrap. Because they had a completely different number system than we did. And you will also notice it was bullcrap because it was 6 years ago, and we're all still here. Much like every other doomsday prediction is all wrong. Because guess what? We're still here. Sadly, we're still here. Right? Okay. Have I heard about what? No. if aliens were to come here, if I were the head of the aliens, the first thing I would do is like, oh my God, get the raid. We have to keep those insects on that planet and not let them leave. Because those morons can't even take care of the one planet they have, let alone letting them off of it. Right? The real problem, you know, there's jokes on TV like, you don't want that family moving into your neighborhood. The universe doesn't want us leaving our neighborhood. Trust me. I wouldn't. I can only hope that one day the aliens come and say, we told you so. Right? Anyway, that's another story for another day. Very fifth wavy. If you haven't read that book or seen that movie, then that joke means nothing to you. But if you have, it was a bit of a spoiler. Sorry. The counting numbers. 1, 2, 3, up to what? Infinity. Now, some people like to write infinity as n, just some number way off up there. Everybody cool? Now, infinity is a weird concept because we can't ever really get there. So even though we say infinity, it's not actually a number, is it? Because there's always the next number. We just don't have names for them. Okay, everybody cool? I don't know the numbers past nonillion. I don't even know what they call the 10 one. I think it might be decillion, but I'm not sure. Everybody cool? And that goes on forever, but it starts at 1. Yeah? All right, next group. Whole numbers. Now, you know what? Yes, Lasso? Okay. You know that whole numbers, you have heard us use that in math, in fractions, yeah? That's not what it is. When we're talking about the number system, the whole numbers are the next smallest group. Sorry, next biggest group, because we're getting bigger. And the whole numbers are the natural numbers. So everything from up here plus 0. So it's 0, 1, 2, 3, up to n. Everybody cool? It is exactly one number bigger than the natural numbers. But they still both go to infinity. Everybody okay? Yeah? Once, twice, thrice? Okay. The integers are the next biggest group. So if I was doing you know those little Russian dolls that you put in an egg and they get bigger and bigger and bigger and bigger? These guys are the little one. These guys are the next bigger one. These guys are the next bigger one. And if you're a natural, you will fit into whole. If you're a whole, you will fit into integer. Everybody cool? Okay. So the integers, now, you should be figuring this out. If the whole numbers were the naturals plus something, then the integers are going to be the wholes plus the naturals plus the negatives. So it's negative n ... negative 1, 0, 1 ... positive n. Is everybody cool? It's easy peasy, yeah? Okay, now here's where it gets a little bit weird. What do you notice is not mentioned in any of those three? Amrit. No decimals. And if there's no decimals, there's no fractions. Okay? Everybody cool? But obviously decimals and fractions exist, don't they? That is where we get into rational numbers. Now, the reason you people start to have trouble with math is because until about grade 3, you are only dealing with the whole numbers, aren't you? Right? You go to school, takes you 10 months in kindergarten to learn to count to 10. Yeah? According to the BC government. Everybody's cool with that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Many of you also know counting from your parents. Now, when I was a kid, go clean your room. No. Go clean your room. No. Go clean your room. No. Go clean your room. Okay. Right? Nowadays, go clean your room. No. Go clean your room. No. Go clean your room. No. 1. And then you were like, what is this new game? And you went to clean your room. And then eventually you figured it out. Go clean your room. No. Go clean your room. No. Go clean your room. 1. No. 2. And then you went and cleaned your room. Then eventually you figured it out. 1. No. 2. No. And then your mom was like, damn it, they figured it out and I'm not allowed to hit them. 2.5. And then you're like, ah! And then you went and cleaned your room. Right? This happened to all of you. If you were Canadian, if you were raised in Canada by Canadian parents, they started fractions on you at 2.5. And yeah, no, I know. My parents, it was 1, 2, 3 was what it was. But that's just me, right? So, that's when you all learn fractions. And all of a sudden, from your parents or grade 3, you found out that it was not indeed 1, 2. You found out that between 1 and 2, there was another infinity. And that is why math started to get difficult for you. Because those fractions are every single number we have exists between 1 and 2. Right? Technically, if I went halfway to 2, and then halfway again, and then halfway again, and then halfway again, would I ever get to 2? No. And that is why math is confusing to us. Right? It's crazy enough to think of regular infinity. 1, 2, 3, 4, 5, 6, counting to infinity. But then counting to 1, and then counting to infinity, and then 2, and then counting to infinity, and then 3, and then counting to infinity. It's crazy, right? So the rational numbers are these numbers. They are fractions. Every single fraction is automatically a rational number. Automatically. All right? If it satisfies a couple of rules. It has to look like this. It has to have a numerator and a denominator. X and Y must be integers. And Y cannot equal 0. If those conditions are met, you have a rational number. Everybody cool? So I'm going to write a couple of them in hot pink. You're just going to say in your head, not out loud, if it's a rational number, okay? Everybody ready? All right. 3/4. Rational or not? In your head. Oh, absolutely, rational. Excellent. 2 3/4. Rational, obviously, because of course that is actually 11/4. Right? Okay. 2.1 over 3. Irrational. Really? Isn't that 2 1/10 over 3? Isn't it? Isn't it? And isn't that 2 1/10 divided by 3? And isn't that 21/10 times 1/3? Which means, isn't that 21/30? Rational or irrational? Rational. Everybody with me? Now, all of this I did here, is any of this news to any of you? Thinking about it this way might be news to you, but all these concepts are not news to any one of you, are they? Right? So again, I say, you must understand what is going on. Because this is just integer over integer, isn't it? Is everybody good? Okay. So that covers now half of this situation, yes? We've now covered all the fractions. What's missing? Decimals. We got to talk about decimals. So the fractions, fine. The decimals are rational if they meet a couple of conditions. One, they must terminate. Now, in math we say terminate. In English, we say end. What do I mean by that? 1.35. Is that rational? Yes, because it ends. It stops at the 5. This is actually 1 35 100ths, which is actually 135 over 100. Everyone cool? So obviously that, if it equals that, is rational. Everybody happy? Okay. The other thing that they must do, if they do not terminate, they repeat. So, is this rational? 1/3. 1 over 3. They're both integers, yeah? If you turn that into a decimal, what do you get? 0.333 repeating. Since that's rational, this also must be rational. Is everybody cool? Yeah? Okay, so now I'm going to write a couple of numbers over here, and you just in your head, rational or irrational, okay? Everybody ready? Rational. Rational. Guaranteed irrational? What if the 300th decimal place is 7 and then it starts repeating? Then what is it? Then it's rational. So this appears to be irrational. Do we know? No. Okay, good. What about this? Rational, because that bar means what? What repeats? Just the 4. What if the bar were to go to there? 374 would repeat. What if the bar were to go all the way? 255374. What would the next 6 digits be? 255374. Everybody's good? All right. So now we have covered every number we could possibly need. Yeah? But I've got one last category here, yes? What is it? Irrational numbers. Well, obviously, irrational numbers are anything that doesn't fit into one of the other categories, yes? So every other number that exists that doesn't fit into one of these categories. Most of them, the most famous one we've already dealt with, what is it? Pi. Because pi never repeats. At least not in our existence. There's a computer that has been dividing a circumference by a diameter since like the 60s. It's up to trillions of decimal places for pi. There is no pattern. So pi is a famous one. There's a lot of others. There's one that is this, e to the x. You've seen it on your calculator. It is 2.78, and it goes on forever and ever and ever. We use it in finance a lot. You'll see it in grade 11. Those are two famous ones. But more likely, you're going to see these. Square root of 2. If you punch that into your calculator, you get 1.414, and the whole screen fills up, yes? Whole screen fills up. Does it repeat? No. What's the only reason it stops at 2? There's no more screen. All right? So if you do a square root and your screen fills up, you have an irrational number. So is the square root of 3. What's that? Irrational. Square root of 4. What's that? Rational. Now I'm going to give you a trick one. Everybody ready? Square root of 1.44. Tricky one. It's rational, right? Because it's what? 1.2. This would be 1.2, which is 1 2/10, which is 12/10. Is everybody cool with the number system? Yeah? Now, you'll notice that I've conveniently saved this lesson for a Friday, yes? Why? Because it's Friday, right? This is pretty easy, yeah? Okay. I want to do something new on a Friday if I can avoid it. So, we're going to do just page 86. You're going to do page 87, and trust me, it's going to be super easy. But there's a couple of weird things here. Some of you are really good on page 86. Some of you are not, so I got to show it to everybody. Convert this to a fraction. What is it? Pardon? 12/100ths. Everybody knows that, right? And what would you do if you saw 12/100ths? Simplify it to what? 6/50ths, and then what? 3/25ths. Is everybody cool? Everybody remembers how to do that, right? What if I gave you 1, 2, 3, 4? What would that be as a fraction? 1, 2, 3, 4 over 10,000. And then I'd simplify. Everybody can do the easy ones, yeah? Now, when I say easy ones, I don't mean that this is easy to simplify. I mean it's easy to convert a decimal that ends into a fraction, yes? We can all do that? Okay. What's different here? It's repeating. Now, some of you already know this trick. Who knows what this is as a fraction? 1/9, yes? But some of you will be like, well, why? This is why. What is 0.1 as a fraction if it just ends? 1/10. Agreed? All right. Well, 0.1 repeating is 0.11111 forever, yes? That is slightly bigger than 1/10, isn't it? Right? Like 11 cents is slightly bigger than 10 cents. Everybody gets that, right? Okay. So we know that it has to be 1 over something because it's a 1 there, just like 12 was 12 over 100, yeah? And I know for it to be rational, this denominator has to be an integer, correct? Right? So if it was 0.1, it would be 1/10. So I need the next integer that is slightly bigger than a 10th. And it's a 9th. Everybody gets that, right? If you have a pizza and you cut it into 9 pieces instead of 10, the pieces are slightly bigger. Everybody understands that, correct? Going once, twice, thrice. Okay. So what would this be? First of all, is that guaranteed rational? No. Does it appear rational? Yes. It appears to be 0.2 repeating, correct? So what would it be as a fraction? 2/9. Excellent. Now, what's different about D? Just what? Just one number repeats. It is not 545454, is it? If it was this, then what would it be as a fraction? 54 over 99, right? But it's not that. What is it? Does anybody know this trick? Adrian? It is 49/90ths. Adrian, can you explain how you've got that, or is that just a trick somebody taught you? It's a trick Cho taught you? Cho, you sneaky. There's a trick here, okay? I'm just going to give you the trick because it's Friday, and this very rarely happens. The trick is this. When it was one number repeating, I put it over 9, correct? Two numbers repeating, it has to be 99, right? How many numbers repeat here? 1, so there's 1, 9. Nothing else repeats, correct? What number do we use for nothing? 0, right? Now, 54 doesn't all repeat, does it? But the 54, what part of that doesn't repeat? Minus 5. Okay? Now there's a long and involved math reason why that works. But this is a Friday class. And it's so not important, I'm not going to bother. Know the trick. Everybody okay? All right. Now, this page, you're going to need your calculator a little bit, maybe. Everybody know how to do a cube root on their calculator from the first unit? Everybody remember? You might have a key on your calculator that has a little 3 there. Okay? You might have a calculator key that has an X there. If you have an X there and you have a forward calculator, it's 3, that key, negative 14. If you have a backwards calculator, it's negative 14, that button, 3. And when you do that, what do you get? Everybody should do it, because that's the only one that's difficult here. Does the screen fill up? So is it rational or irrational? Irrational. All I want you to do for these 7 is tell me if they're rational or irrational. Go. It should take about 10 seconds. But notice I want you to put them in the categories. If it fits into one of those 4 categories I gave you, you only write 1. What if it fits into 5 of them? Then you write all 5. Is it possible for a number to fit into all 5 of them?
Yeah. Wait, no.
No, because if it's irrational, it can't be any of the others. Go. Literally, it should take like 5 seconds. You have a forward calculator? Yeah. So it's the same thing. So we're going to push, we wanted the cube root, right? So we're going to push 3. And then on yours, it's in math. See right there? There's a cube root. See, number 4? So now what I've done, Indigo, I pushed 3 already. So I've got to use 5. See? If I push 5, see, cube root of negative 14. But you didn't need to push 3 on our calculators. You could have gone just into math and used the cube root right there. That math key for you is very powerful, as you can see. Right? So I'm going to peel my orange. When I'm done peeling my orange, I should have answers to all of these. Because this is a Peruvian mandarin. They peel very easily. Although, for some strange reason, the Japanese and the Chinese and the Koreans can grow mandarins with no seeds. But the Peruvian mandarins sometimes have seeds. And they don't have enough seeds to expect it every time. So you'll bite into it and it's like, oh, this is delicious. And then you'll hit an orange seed. And orange seeds taste disgusting. They ruin the whole wedge of orange. At least I think they do. You might disagree. But I have learned that with these Peruvian mandarins, you can hold them up to the light. And then it doesn't fool you. No seed. No seed. No seed. No seed. No seed. No seed. No seed? No seed. No seed? Score. The one I ate earlier had 9 seeds. It wasn't pleasant. All right. What's this? It's rational. What else? It's an integer. What else? It's a whole, and it's a natural. Because it's 5. Right? What's this guy? Rational. Why? It ends at a 4. What is it as a fraction? 319,754 millionths. Which is just a fun word to say. Yeah? Okay. Tricky. What's D? See, I bring exponents back to mess with your head. It's 16, right? So it's natural. If it's natural, does it fit all the way down? Yes. Everybody good? What about 9? It's natural. So does it fit all the way down? Excellent. What about F? Of course it doesn't work. Why? There is no way you can get a square root of a negative number, is there? This is your imaginary numbers. And sometimes physics gets, and especially electricity, gets so complex that you need to do this, even though this doesn't really exist. You guys will 99.9% never need to deal with imaginary numbers. 99.9%. What about that one? Rational. Appears rational, right? What if the 372nd decimal is a 4? Then it's irrational, right? But as it appears to us, it is rational. Everybody cool? All right. So listen. All I want you to do, and you've got like 40 minutes now, is do page 87. That's it. That's all. I'm going to walk around and get your quiz scores from yesterday. That was out of 12? 12. Right? All right. And then, if there's time, I'll show you shark camouflage. If you care. But let's be honest, it's not math, so all of a sudden you'll all care. I care. Are you scared of sharks? No. Good.